Hey everyone, and welcome back to Deconstructed Build. Today, we're not just looking at how things are built, but why they stay up. Have you ever walked into a new building, seen those massive steel beams spanning huge spaces, and wondered, how do they know that won't just bend and snap? Well, that's exactly what we're going to deconstruct today. Structural engineers don't just guess. They perform a series of crucial calculations. They essentially put every beam through 3 rigorous tests on paper before it ever leaves the factory. These tests ensure our buildings are not only strong, but also safe and comfortable. Think of it like this. A chef has a recipe with 3 main steps to make a perfect cake. If any step is missed or done wrong, the cake fails. Our beam design is similar, with 3 critical steps: bending, shear, and deflection. Let's start with bending. This is probably the most intuitive one. When you put weight on a beam, it wants to sag in the middle, right? That sagging is bending, and if it bends too much, it could fail catastrophically. Engineers use something called the section modulus, or Z. This Z tells us how resistant a beam is to bending. The bigger the Z, the stronger it is against bending. The formula is quite elegant. Z equals M is the bending moment. Essentially, how much turning force the load is creating, and F is the allowable stress for the material, like steel. Loads come in different forms. A single, heavy point load, like a column landing on a beam, or a distributed load, like a concrete slab or people spread across a floor. For a point load in the middle, the maximum bending moment is WL4. For a distributed load across the whole span, it's W8. Let's take an example. Imagine a 4-meter steel beam supporting a really heavy wall, say 200 kilonewtons, which is about 20 tons of force, distributed evenly. After plugging that into our formula, we find we need a beam with a section modulus of at least 606 cubic centimeters. So, the engineers consult their tables and pick a universal beam 305 times 127 times 48 kilograms per meter. This beam actually gives us a Z of 612.4 cubic centimeters, just over what we need. It's a pass for bending. Next, we tackle shear. While bending worries about the middle, shear worries about the ends of the beam, right where it connects to columns or walls. Imagine trying to tear a piece of paper. You're applying a shear force. For a beam, this is the force trying to slice it vertically, often at the supports. The key part of an I-beam that resists this vertical tearing is called the web. That's the thin vertical section in the middle of the I. Engineers calculate the area of this web. For our chosen beam, that's 2,762.56 square millimeters. The maximum shear force in our 20-ton load example would be 100 kilonewtons at each support. We then calculate the average shear stress by dividing this force by the web area, our result. About 36.20 newtons per square millimeter. Now, grade 43 steel, a common structural steel, can safely handle up to 110 newtons per square millimeter. Our beam is well within that limit. Another pass. Finally, we come to deflection. This is about how much the beam sags. Even if it's strong enough not to break, bending or tear, shear, too much sag can lead to problems like cracked plaster ceilings, bouncy floors, or even doors not closing properly. It's often more about serviceability and comfort than outright failure. The industry standard is that a beam shouldn't deflect more than 1/360th of its span. For our 4-meter beam, that means a maximum sag of about 11.1 millimeters, or just over a centimeter. Calculating deflection is a bit more complex, using the formula 5WL3-384EI. Here, we introduce 2 new heroes: Young's modulus, E, which tells us how stiff the material itself is. Steel is very stiff. And the second moment of area, I, which tells us how effectively the shape of the beam resists bending. An I-beam, for instance, is incredibly efficient at this. When we crunch the numbers for our beam and its 20-ton load, the calculated deflection is only 8.35 millimeters. That's well within our 11.1 millimeter limit. A clear path. Now, before we wrap up, it's one thing to see a design that works, but it's another to see how engineers problem solve when things don't work. Let's run through 5 critical scenarios, our design gauntlet, to see how these calculations dictate the build. 1. The bending gauntlet. First, we look at bending. The rule here is simple. Section modulus equals maximum bending moment divided by the material stress. We'll use a standard steel stress of 165 Newton per millimeter squared. Problem A. The heavy point load. Imagine a 5-meter beam with a massive 50 kilonewtons internal column landing right in the center. The math for a center load. The bending moment equals load times length divided by 4. That gives us 62.5 kilonewtons per meter. The solution. We divide that 62.5 million by our 165 stress limit. We find we need a section modulus of 378.8 centimeters cubed. If our current beam is smaller than that, it fails. We must swap it for a beefier profile ... Problem B, the distributed load. Now, take that same 5-meter beam, but instead of a column, it's supporting 100 kilonewtons of floor weight spread evenly. The math. Here, the bending moment equals total load times length divided by 8. The result, even though the total weight is double the previous example, the result is the same, 62.5 kilonewton per meter. The lesson. This deconstructs why architects love distributed loads. You can carry much more weight with the same beam size just by spreading it out. 2. The shear check. The problem. Sometimes a beam is strong in the middle, but tears at the ends. We have a 100 kilonewtons force pushing down right where the beam meets the wall. Our beam has a web area, that vertical middle slice, of 2,762.56 millimeters squared. The math. We calculate average shear stress by taking the shear force and dividing it by the web sectional area. The solution, 100,000. Newtons divided by 2,762.56 gives us 36.20 Newton per meter squared. Since steel safely handles up to 110, this beam is a total pass. It's nowhere near the tearing point. 3. The deflection gauntlet. Finally, we check the sag. Our serviceability limit is the length divided by 360 for a 6-meter beam. Any sag over 16.6 millimeter is a failure. Problem A. Point loading. We place a heavy load in the center. The math. Deflection equals load times length cubed divided by 48 times material, stiffness times the shape's second moment of area. The result, if that math spits out 18 millimeter, the beam fails. It's safe, but your floor will feel like a trampoline and your plaster ceilings will crack. Problem B. Uniformly distributed loading. We spread that same weight across the whole 6-meter span. The math. The formula shifts to 5 times load times length cubed divided by 384 times. Stiffness times shape efficiency. The solution. Spreading the load drops our sag to roughly 11.2 millimeter. Because 11.2 is less than our 16.6 limit, the design is now a pass. By running these 5 checks, we ensure the build isn't just standing, it's performing exactly as intended. So there you have it. Our universal beam, 305 times 127 times 48 kilograms per meter, under a distributed load of 200 kilonewtons over 4 meters, successfully passed all 3 critical checks: bending, shear, and deflection. This methodical approach is why you can trust the buildings you inhabit. Every structural element, from the smallest joist to the largest girder, undergoes this kind of rigorous analysis. Tall. It's a testament to the blend of science, mathematics, and practical experience that goes into every single deconstructed build. I hope this gave you a new appreciation for the unseen work that makes our modern world stand tall. What other engineering marvels would you like us to deconstruct? Let us know in the comments below. Don't forget to like this video, subscribe if you haven't already, and hit that notification bell so you don't miss our next deep dive. Thanks for watching, and we'll see you on the next deconstructed build.